Bom, boa tarde a todos. Espero que todos estejam bem, se cuidando, com saúde. Hoje a gente tem mais o último seminário desse ano. E a gente tem um convidado internacional, então eu vou passar agora falando em inglês. E no final, após o seminário, a gente volta a falar em português, tá? Então, se quem tiver perguntas depois, a gente vai ter que ser em inglês, ok? So, hi everybody. Good afternoon in Brazil, but I think in Germany it's good evening. So now I hope everybody, each one of you are fine, taking care of yourself, physically and mentally. So the seminar of today will be given by Dr. Bertram Bitsch. Dr. Bertram has a master's degree and a PhD in physics from Tübingen University in Germany. He was a postdoctoral researcher at Nice Observatory in France. Then he was a senior research fellow at Lund Observatory in Sweden. And now he is a research leader of an ERC Grant Pandora at Max Planck Institute for Astronomy in Germany. His research focuses on computer simulations of accretion disk structures and planet formation. And today, Dr. Bertram will talk to us about planet formation in protoplanetary disks. I'd just like to remind everybody that if you have any comment or question, please write in the chat, and then at the end of our presentation, I'll call you to make it in person. So Bertrand, you may start your presentation, please.
Yes, thank you. Let's see. So wait. Good. So you can see my presentation now, right?
Yes, we can.
Yes. Oh, perfect. Okay. Thank you very much. Thank you for the invitation for me to give this talk. So I will talk a bit about planet formation in protoplanetary disks, which of course is a bit a very general title, because we all know that planets form in protoplanetary disks. But the idea of this talk is to focus a little bit more on the disk aspect of planet formation. So to start my talk, I of course would like to quickly introduce the exoplanet observations. So this is a plot that is already actually a few years old, but essentially in this plot not too much changed, except that we have many more exoplanets detected in the last 5 years. But the general trend of this plot is basically essentially still the same. So what you see here is the orbital distance in astronomical units against the planetary mass in Earth masses. In black, you have the planets in our own solar system. There's no Mercury and Mars because they're just too small to be on this scale. And this, of course, already tells you something about the difficulties of observing exoplanets. It's very difficult to observe the small planets. If you look at this plot, you can identify 3 main groups of planets. There's the cold Jupiter, similar to our own Jupiter in planetary mass and orbital distance. And there's the hot Jupiters, which are also Jupiter mass planets, but very, very close to the star. So they orbit the stars in just a few hours or a few days. It's very hot, hence they're called hot Jupiters. And we have this class of planets. There's just a few Earth masses, and these are the so-called super Earth. So basically think of like an upscale Earth planet. And in this talk, I would like to focus on the formation of these super Earths in the protoplanetary disk. So before talking about the formation, I would like to present a few statistics about the super Earths. So this is how I imagine these guys would actually look like. So they are like, in this talk, we can think of something like 1 to 4 Earth radii and about up to 20-ish Earth masses. And these planets are very, very common around stars. So basically, statistics tell us that basically 1 out of 3 solar-type stars should actually have a super Earth, or maybe even more. So these super Earths are actually really, really very common in the inner systems. Then these super Earths are actually often multiplanetary systems. You can see here in this plot on the right from Weiss et al. 2018, some systems detected by Kepler, and then also follow up by radial velocity. So what you see here in this sketch, you here have first the solar system. So these are the terrestrial planets in our solar system. And you see that these super-Earth systems mostly consist of planets that are much closer in to the central star. And in addition, you actually can recognize some patterns. For example, if you look at this system down here, you see that all these planets seem to have the same size. And the same size can also be, to some level, translated into the same mass. So there seems to be a correlation that these planets in these super-Earth systems actually have similar sizes and masses. And this is an interesting property that we have to capture in our formation simulations. So the outline of my talk is how do super-Earths form a protoplanetary disk. For this, I would like to present you the formation scenario that we are working in. We'll talk about the structure of protoplanetary disks, then, of course, about the super-Earth formation, and then a little bit about if the water ice line could actually be the birthplace of planets. So let's get started. So how do planets form? So we have a star and we have a protoplanetary disk around this star. This disk consists of small micrometer-sized dust grains that can actually grow in this disk by coagulation and condensation to pebbles of millimeter, centimeter in size. Then these pebbles can form planetesimals, so objects of 100 kilometer in size by gravitational collapse. Then these planetesimals can accrete leftover pebbles for other planetesimals to form planets. If the planets become big enough, you can actually form gas giants, so you have to make a core of several Earth masses and can then accrete the gas onto that core. During this formation process in the protoplanetary disk, the small planets migrate in the type 1 migration. So you see here from a simulation, the planet, you have the spiral arms here, and that would actually exchange a torque between the planet and the disk, and the planet starts to migrate. But the bigger planets, they actually carve gaps in these protoplanetary disks, and they would migrate in the type 2 migration regime. And all of this you have to put together, and at the same time you have to take care of the disk evolution, so the disk evolves, and then later on you put this all in a simulation. You compare this to the exoplanet populations that you can actually observe. There you have to care about your super-Earths, your giant planets, and you actually have to care about the composition of these planets, so if this is actually made of the right materials. And if you say like, I'm very confused and this is all a complicated process, and you can lose a lot of hair while trying to go through this process, then I absolutely agree with you. So it's a very complicated process, and I would like to highlight a few things that actually go into this formation process before going into the details of the simulations. So importantly, as I said in the first step, the grains grow in the protoplanetary disk. So this is a plot from Güttler et al. 2010, which just looks at different growth mechanisms for particles. So here you have two columns. So you have equal sized particles and one small and one big particles, and there are different outcomes of the collision regimes depending on the velocity at which these particles would collide. I mean, you can very easily imagine if you have two particles that come at very low speed, they might actually hit and stick. But if you have a very fast speed between the particles, they might just collide and fragment at the other end of this table. So what really matters here for the sticking, what happens in your coagulation regime is actually the speed between the particles. So the relative velocities between the particles determines the outcome of these collisions. If you have a hit and stick, so a growing collision, or a destructive collision. And if you put this all together, you can actually calculate grain size distributions in this protoplanetary disk that you see illustrated here. So this is basically just the surface density of these grains as a function of the grain size in centimeters for one simulations. You see here two different simulations. One is the classical MRN distribution, and the other one comes from this Birnstiel 2011 paper, where they account for different mechanisms for the growth of these particles. So these, as I said, these particles can grow through the coagulation, but once they become large, these particles can actually start to fragment because the relative velocities increase. And the maximal grain size is given by this equation here. So the maximum grain size is a function of the disk surface density, the disk viscosity, which sets the level of turbulence, so the speed between the particles that collide, the density of the particle, this parameter UF, which is the fragmentation velocity, which is basically a property that is measured in the laboratory experiment. So basically, if you have grains that would collide, then you just measure at which velocity, if these two grains collide, would they actually fragment. And CS is, of course, the sound speed in the protoplanetary disk. So this fragmentation velocity is typically between 1 and 10 meters per second. This really, as I said, comes from laboratory experiments. And we will come back to this towards the end of my talk. Now we have the grains in the protoplanetary disk. These grains actually also interact with the gas part of the protoplanetary disk, and they actually drift through the disk. And this is related to the fact that the disk is hotter and denser close to the star, so we have a radial pressure gradient in the protoplanetary disk. And this radial pressure gradient actually mimics a decreased gravity that acts on the gas, so the gas actually orbits slower than the Keplerian velocity, so the gas is orbiting the sub-Keplerian. You see this here in the equation, so the velocity of the gas is basically the Keplerian speed minus eta times the Keplerian speed, where this eta parameter is given here. Is a function of the disk aspect ratio and the local radial pressure gradient in the protoplanetary disk. However, the particles, so the dust particles in itself, they don't feel this pressure gradient force and want to orbit on a Keplerian speed, which means the particles actually feel a headwind from the gas, which removes angular momentum from the particles, so these particles spiral in through the disk on very short time scales. So the particles in the disk, they move inwards. Now we have to think about how we can actually make these planetesimals. I will not go into the details how to make planetesimals, but there's many different ways how you can do planetesimals. But the underlying process is basically always the same. You have to concentrate these particles in a cloud of pebbles that can then undergo a gravitational collapse to form these planetesimals. There are different ways. You can collect the particles with these small-scale eddies in pressure bumps in the protoplanetary or in vortices, or you can do it via the streaming instability, which is basically a self-feeding instability that relies on the velocity differences between the grains and the particles. I recommend a lot of literature, as you can see, but here's a very nice summary from the Johansen et al. 2014. Which was on the Protostars and Planet 6 conference, and there's actually also the video of his talk that you can look at it online. Bottom line is these pebbles, when you make these pebbles cloud, they can gravitationally collapse and can then actually make planetesimals with a characteristic size of about 100 kilometers. Now these planetesimals can grow further by the accretion of pebbles. And this is illustrated here in this cartoon. You have our planet here in black, and in red is the Hill sphere of the planet. Now, if we had a planetesimal that would enter within the Hill sphere, is actually mostly scattered away. And this is a process that is actually very common, because for the planetesimal to be accreted, you would actually have to hit this blue circle, which is the gravitational cross-section. So the planetesimal accretion is actually quite inefficient, especially in the outer disk region. So if you go beyond a few AU, planetesimal accretion just takes very, very long, and it's very difficult to build large planetary cores via planetesimal accretion. On the other hand, the pebbles, as I said, they actually feel the gas friction, so they lose angular momentum due to the interactions with the gas. So if a pebble enters the planetary Hill sphere, it can actually be accreted very efficiently by the planet because the pebble loses the angular momentum due to the interactions with the gas. And this can then give a very large accretion rate. So you see the accretion rate here in this equation here, where tau f is the Stokes number of the particle, which basically is a measurement of the size of the particle. So the larger the particle is, the larger is the Stokes number. Then the Hill radius is basically a measurement of the size of the mass of the planet, because obviously the more massive the planet, the bigger the Hill radius. And the pebble surface density, so how many pebbles do you actually have? In most common equations, the pebble surface density is proportional to the square root of the pebble flux, so how many pebbles flow through the disk as a function of time. Now, how does pebble accretion, what is the word, work in the sense of how fast do you build your planetary cores? And you see this here. And this plot on the left-hand side, where you have the planetary mass of your planetary embryo in Earth masses versus the accretion rate in Earth masses per year. So if you start with something that is just 100 kilometers in size, you actually see you have to follow the black line. That is the real pebble accretion rate. You see that your pebble accretion rate is something like 10 to the minus 12 Earth masses per year, which of course is very, very low. And it's not enough to grow your planet during the lifetime of the protoplanetary disk. But if you increase your planetary mass to something like the mass of Ceres, you already arrive at accretion rates that are start to be compatible with the lifetime of protoplanetary disk. So the bottom line here is, even if you have pebble accretion that can be very efficient, you need a core that is big enough to accrete these pebbles efficiently. And you see, once you reach something like the moon mass, you see that your pebble accretion rate is around 10 to the minus 5 Earth masses per year. So within 1 million years, you can grow to 10 Earth masses. And this is what you can also see here on the right-hand side. So if you start with a planet that is already 10 to the minus 5, 10 to the minus 4 Earth masses, you see you can reach masses of around 10 Earth masses within 1 million years. So the bottom line here is, for pebble accretion, the initial mass of your planetary embryo matters. And for that, you might actually need initial collisions between planetesimals. So in the outer disk, you can imagine that you first form your planetesimals, maybe like 100 kilometers in size. These planetesimals then collide to make something bigger, something between the mass of Ceres and the moon, and then pebble accretion takes over and finishes to build your planetary core. Now, when does pebble accretion stop? This happens at the so-called pebble isolation mass. And this is when the planet starts to influence the gas structure that the planet actually grows in. So you see here in this simulation, the planet, and the color coding gives you the density relative to the unperturbed density. So the planet, as it starts to grow, it pushes away material from its orbits by the exchange of angular momentum with the protoplanetary disk. What happens is, if your planet pushes away material exterior to its orbit, it gives angular momentum to that material, so it basically accelerates the material exterior to the planet. This is what you can see in this plot here on the right, where you have the planet at 1. And the y-axis gives you the azimuthal gas velocity divided by the Keplerian velocity. So 1 is, of course, the Keplerian velocity. So on the outer parts of the protoplanetary disk, where the planet has no influence, the gas velocity is sub-Keplerian because of the radial pressure gradient. This means your pebbles would just drift inwards, as I explained to you before. But exterior to the planet has accelerated the gas to super Keplerian velocities. This means if your particle that comes in from the outer region reduces the angular momentum because the gas is sub-Keplerian, then suddenly it reaches this region exterior to the planet where the gas is super Keplerian. This actually means the particle would be accelerated outwards. And this means the pebble stops in this region exterior to the planet. And if the pebbles are trapped exterior to the planet, they can, of course, not be accreted onto the planet anymore. So pebble accretion actually self-terminates. And this is very important, because once the pebble isolation mass is reached, then maybe you can start thinking about contracting your planetary atmosphere. The pebble isolation mass in itself is a strong function of the disk parameters. So it depends on the disk's aspect ratio, the viscosity, the radial pressure gradient, and of course also on the Stokes number of the particles. Generally, you can say that this isolation mass is small in the inner disk and larger in the outer disk, because the pebble isolation mass is a very strong function of the disk aspect ratio. So the point here is that the planet changes the disk structure, and by changing the disk structure, you change how the particles would move in the disk. And if your planet becomes massive enough, it exerts a pressure bump exterior to the planet where you can trap your pebbles and prevent them from being accreted onto the planet. This is the same mechanism that is also used to explain a lot of these wonderful ALMA images where you have your disk with the rings, where people then say, oh, maybe it's a planet that basically generates a pressure bump, where you then accumulate the particles that give you these bright rings. It's exactly the same mechanism. It's just a mechanism. But it also has not only the ability to explain the rings in the ALMA images, but it is also very important for planet formation in itself. Now, I would like to talk a bit more about the simulations we did for the protoplanetary disk structure. As I mentioned, so this is HL tau, actually. And you see here, of course, the different rings where planets could be one of the main drivers of these structures. But if you look here at the size bar, so this is 14 AU, you actually see, well, this is basically just this bright blob in this image. And in the inner disk, this is where we actually think that these super Earths formed. So we cannot really rely only on the observations to tell us something about the structure in the inner disk. This is why we have to rely on the simulations in the of the inner disk regions for our models of super Earth formation. And this is what I would like to focus on in the next couple of slides. So for the simulations in itself, we use 2D hydrodynamical model that includes viscous heating, radiative cooling, and stellar heating. We have by 2D, in this case, I mean radial and azimuthally. So we have also the vertical component. And this is actually very important in order to capture the heating processes in the disk correctly, because you can imagine that the stellar irradiation can be absorbed by certain bumps in the disk that then change the underlying structure. So you see this here illustrated that we have a central point source, and these arrows here indicate how the stellar irradiation actually would go from our central star. And if we actually have some material in the disk that would absorb the stellar irradiation, we can actually cast a shadow in the outer parts of the protoplanetary disk. And this is something for that you really need the 2D geometry in order to study this properly. So doing this, I would like to go a bit into the model, what goes into this modeling. So as I said, we use 2D simulations with the radiative cooling, viscous heating, and stellar heating. In our approach, we use a constant accretion rate through the disk. So our m dot is constant. And this has actually some very important consequences for the structure of the protoplanetary disk. So first, I would like to focus here on this plot on the top right, where we are showed the opacity of the dust grains as a function of the temperature. In this case, I show the Rossland mean opacity, which is directly responsible for the cooling. So the cooling rate in the protoplanetary disk is inversely proportional to the Rossland mean opacity. This opacity has a transition here at the around 170, 180 Kelvin, which is the transition at the water ice line. So in the cold parts of the disk, of course, you have your water grains, but then if you go to higher temperature, the water evaporates and you basically lose the contribution of the water grains to the opacity, which explains this drop in the opacity here. Now, if you have a change in the cooling rate at the water ice line, we actually change directly the temperature. You see the temperature here in the bottom plot. The red line here is from our simulations, and you see that around the water ice line, we have a change in the slope of the temperature. And this is directly related to the change in the opacity around the ice line. Now, if we have a change in the temperature, this actually means we have a dip in the surface density at the same time. And the reason for that is if you change the temperature, we change the aspect ratio of the disk, and when we change the aspect ratio, we change the viscosity of the disk. But since we construct a disk that has a constant accretion rate through the disk, if we lower the viscosity, we have to increase the surface density and vice versa. So basically a change in the temperature directly relates into a change in the surface density. More precisely, if you have a bump in the temperature profile, we get a dip in the surface density profile. And this is has very important consequences for the growth and for the migration of planets. Now we can relate actually this accretion rate to a time evolution of the protoplanetary disk, as you see here in this plot. So we show again the temperature as a function of orbital distance. And the different black lines give you the time evolution of the protoplanetary disk. You see that the disk actually cools down in time. Very originally, the ice line is around 5 AU, so where Jupiter is in our solar system at the moment. And within like 1 million years already, you see that the water ice line crosses 1 AU. And this, of course, is a big question if that really happened, and what would that actually mean for the water content of the Earth. Now, in these simulations, I've only showed you one opacity curve that actually corresponds to micrometer-sized grains. So for all these simulations, we've assumed that all the grains are only micrometer in size for simplicity. Now I would like to show you some of our new simulations where I actually relax this assumption. So first, this is the opacity profile for the grains with different sizes. So you see here again in gray, this is the transition at the water ice line, and you see here in color-coded the different grain sizes. So you see in dark blue, this is the opacity for the micrometer grains that we were using before. But if you go to larger and larger grain sizes, you see that the opacity becomes smaller and smaller for increasing grain sizes. And this is because when you change the sizes of your particles, you change the properties of the particles in such a way that the opacities are influenced. So basically, what you basically need to take away from this plot is if you have larger particles, you have a lower opacity. Now, this is all very nice that we have an opacity as a function of grain size, but now we also, of course, want to include the full grain size distribution. For this, we actually have to take our disk structures and calculate basically like a feedback loop, as you see illustrated here. So the computation-wise, we start with an initial disk structure. There's a given temperature, given surface density, and then from this we can actually calculate the relative velocities between the grains. Remember, the relative velocities are mostly set by the viscosity and also by the sound speed. From the relative velocities with the grains, we can calculate the grain size distribution, so how big can the grains become and what is the exact distribution of these grains. From that, we can calculate the opacity of the disk. If we just basically distribute the grain size distribution and calculate the corresponding opacities, as I've just shown you. With the new opacities, we can calculate the stellar heating and the cooling rates, which then would give us a new disk structure. And basically, by iterating on this feedback loop until we reach a thermal equilibrium, we can calculate the disk structure very precisely. Now, what does this look like? You see here the results from our simulation. We have here the aspect ratio and here the temperature. The gray line, as usual, is the transition at the at the ice line. So first, we can focus on the solid lines, which are disks where we assume the particles only have one single grain size. So you see in dark blue the disk with 1 micrometer grain, so where the grains are only 1 micrometer in size. And you see, if you go to larger and larger grain sizes, the disk structure actually changes significantly. What happens is that for the larger grains, your disk actually becomes colder. And this is related to the fact that if your grains are larger, you have lower opacities. And if you have a lower opacity, this actually means you cool more efficiently. If you cool more efficiently, well, you become colder. But if you now look at the two different grain size distributions, the MRN and the Birnschville 2011 grain size distribution, these are the dashed lines. You see these two grain size distributions in itself are very similar. But very importantly, these grain size distributions do not follow the profile of a disk with just a single grain size. And this is very important because it means that if you want to calculate the disk structure properly, you cannot rely on only one single grain size. And this, in this particular example, we use a fragmentation velocity of 1 meter per second and an alpha of 5 times 10 to the minus 3. We also tested a different alpha viscosity parameters. I will show some results soon. But there the trend is basically exactly the same, that you need the full grain size distribution in order to calculate the disk structure properly. And this you can actually really see in this plot here, where I put just one of the grain size distributions. What I show here is the grain size as a function of the orbital distance, and the color coding gives you the contribution to the mean Rostand opacity. So basically, what you can take away from this plot is, for example, if you are at 10 AU, you just follow up this line, and you can see where does the main contribution of the opacity come from? From which grain size does the main contribution to the opacity come from? This is also indicated by these three lines with the 25, 50, and 75%. So you start from the small grain sizes, you go up here at this point. All these grains down here contribute 25% to the total opacity. Here it's 50% and here 75%. So you see that the opacities are dominated by different grain sizes in different regions of the disk. So you see the grains, the opacities is dominated by the smaller grains in the inner disk and by larger grains in the outer regions of the protoplanetary disk. And this is actually related to the fact that you can, from this plot, you see in the outer regions of the protoplanetary disk, the opacities are higher at these cold temperatures that you have in the outer disk. So the opacity has to be dominated by the larger grains. As I said, this basically means that you cannot model this with a single grain size. But very importantly as well is that even if you have a grain size that would dominate the opacity, it does not necessarily mean that this grain size actually dominates the dust size distribution. So for example, you can have a situation where your grain opacity is dominated by the micrometer grains, but at the same time, your dust size distribution is dominated by 100 micrometer size grains. And this is because the grain size distributions and the opacities, they do not follow the same power laws. In the sense that here, as I said, for example, here, if you go from millimeter to centimeters, it's like an order of magnitude in the opacity if you increase your grain size by an order of magnitude. But at the same time, if you have your grain size distribution, you do not necessarily have an order of magnitude more centimeter-sized grains than millimeter-sized grains. And this is why these the grain sizes that dominate the opacity do not dominate the dust size distribution. So we can look at the different alpha parameters. Again, if you have a lower alpha parameters, you can actually grow to larger grain sizes. This is because the relative velocities between the grains are lower. You see this here in this plot, where you have here the aspect ratio of the disk as a function of orbital distance. And here you actually see the maximum grain sizes. These are the top lines, and the 50% contribution to the opacity lines. So again, this is the line. If you just go up from the lowest grains, this is like to which grain size you contribute 50% of the opacities. In this case, a few times 10 to the minus 4. So we can of course identify some general trends in this. From these simulations, mainly that your disk becomes colder if you have a lower viscosity. And this is, of course, related to many things. So the first is like the feedback loop that I was trying to describe to you. So the lower viscosity leads to larger grains. These larger grains have lower opacities. The lower opacities leads to more efficient cooling. And the larger cooling leads, of course, to colder disks. Additionally, of course, if you reduce your viscosity, you also reduce your viscous heating, which also makes your disk colder. We are trying to really disentangle the effects, what actually really causes more to the reduction of the temperature of the protoplanetary disk, if it's that the grains become larger or that the viscous heating becomes smaller. But it was very complicated, and we did not fully manage to do this analytical. Nevertheless, what we provided in this work is actually a very nice fit to the position of the water ice line in the protoplanetary disk as a function of the alpha viscosity parameter, the surface density, and the dust to gas ratio. You see this here illustrated in this plot, where the color coding gives you the position of the water ice line as function of alpha and of the gas surface density. As expected, of course, if you have low surface densities and low alphas, you have the ice line very close to the star. And if you have larger viscosities and large surface densities, you have the ice line further out in the disk. This is the fitting formula that we provided in Savido et al. 2020. And you can use this to compare if you just construct a simple disk model to run your simulations. Now, I would like to talk a little bit about the formation of the super Earths in these protoplanetary disks. So For that, we went even more complicated by including actually more species into our opacity laws. So in the previous simulations that I've shown you, we just had silicate and water, and we now have included many more species in these simulations. Essentially, the opacity law is still very, very similar. So of course, the larger grain sizes give you lower opacities. But what you can also see is that you have some very interesting transitions here at some of the additional evaporations front that we have introduced. But I don't really want to go too much into the detail. So what we then we did our same set of simulations where we calculate the disk structure for a given viscosity. We include viscous heating, stellar heating, and radiative cooling. And we have the full grain size distribution determined where the maximum grain size is determined by the fragmentation limit as we discussed before. You see here 3 different sets of simulations for different alpha viscosities going from 10 to the minus 3 down to 10 to the minus 4 alpha. You see here the aspect ratio, temperature, and the disk surface density as a function of orbital distance. So we focus here really only on the inner UAU in the protoplanetary disk. We tested for 4 different surface densities to mimic sort of an evolution of the protoplanetary disk as function of time. The general trends is easiest illustrated here on the left hand side. So for the simulations that have the highest surface density, we have, of course, the highest temperature in the protoplanetary disk. And this is because we have the most amount of viscous heating. And this, of course, if you have the highest temperature, you, of course, have the highest aspect ratio in the protoplanetary disk. Now, if you go to lower surface densities, you start to see some wiggles in the protoplanetary disk, which are related to some level to the transitions at the different ice lines indicated by all these gray bands. So the dashed one corresponds to the water transition, where you have, if you have like a small bump in the protoplanet in the aspect ratio, your next region might be actually small in the shadow, and then you can generate this bumpy structure in the protoplanetary disk. If you now go to lower viscosities, especially here for the case of alpha 10 to the minus 4, you actually see that all of these aspect ratios and temperatures basically all give the same value. And this is related to the fact that at these low viscosities, your grains become larger and larger, and these larger grains basically have a very tiny contribution to the opacity, so that the cooling becomes very efficient. And in the end, your entire disk temperature structure is dominated by stellar irradiation, which is why these disks have all the same temperature structure, because the stellar irradiation is basically the same in all of these simulations. Now, these simulations featured a fragmentation velocity of 1 meter per second. Now, as I said, the fragmentation velocity can actually be larger. So if you go to 10 meters per second, we basically see not too much of a change for the low viscosities, but for the high viscosities, if I go back and forth, you see that the disk aspect ratios becomes much smaller if you go to 10 meters. Again, this is related to the fact that your grains become larger, and when the grains become larger, they have a lower opacity, and your cooling becomes more efficient. Now, from these disk structures, we can actually calculate the pebble isolation mass in these protoplanetary disks. You see here 6 different panels. So for the 3 different alpha viscosities on the top, we use a fragmentation velocity of 1 meter per second, and in the bottom, we use a fragmentation velocity of 10 meters per second. So for the 10 meters per second, as I said, we have the larger grains and the lower aspect ratios, which then directly translate into lower pebble isolation masses, because the pebble isolation mass, as I said before, mainly depends on the disk aspect ratio. Now, these colorful dots correspond to the masses of inner planets that were observed with Kepler and with radial velocity. So the gray dots are the Kepler mass planets, where we use a mass-radius relationship, and the greenish dots are from radial velocity planets. And what you can see here directly is, if you want to make a disk that has a low viscosity, and you want to explain the bulk of the Kepler masses of these super-Earths at these low velocities in our low fragmentation velocity, low alpha viscosities in our model, you see it does not really work that well because the pebble isolation mass is clearly way too small in order to explain the bulk of these planets. Of course, you could grow via collisions in this case, but then it's very questionable how many collisions you actually really need in order to make these systems. So what you would need is a higher viscosity. For example, here in this case, alpha 10 to the -3, you get nice enough pebble isolation masses that you can explain the bulk of these super-Earths in these from these observations. But now, as we have, of course, the full grain size distribution available, we can actually calculate the pebble accretion rates onto these planets. This is what you see in this plot here, illustrated just for a planet growing at 1 AU via pebble accretion. So you have here the planetary mass as a function of time for a planet accreting by pebble accretion with the given size distribution that you get from our simulations. You see here a difference in these simulations. You have the dashed lines and the solid lines. The solid lines correspond to a fragmentation velocity of 1 meter per second, so you have the smaller grains. And the dashed lines correspond to a fragmentation velocity of 10 meters per second, so you have the larger grains. And you see directly, if you have the low fragmentation velocities and a high level of alphas, you see that your growth time becomes longer than 10 million years, which means it's very uncomfortable if you want to make planets during the lifetime of the protoplanetary disk. So you have to rely on the simulations where you have a larger fragmentation velocity, where you can then grow your planets actually in quite a short time scale. But if I go back, these are the bottom simulations in this plot, which actually means your pebble isolation mass is quite low. So we have a good enough growth time for planets that would form as an alpha viscosity, and this with alpha viscosity 10 to the -3, but then we just barely reach around 5 Earth masses with these simulations. So we have to, from these simulations, it seems that there seems to be a trade-off between the pebble sizes and the pebble isolation mass to explain the super Earth population that we observe. This, I think, is very curious, because this is something that has not been paid attention to in previous simulations, where people either assumed a fixed disk structure and then calculated from that fixed disk structure their pebble sizes. But by combining the correct pebble sizes with the thermodynamics of the disk and to then calculate the planet formation rates, we actually see that there seems to be only a very narrow region of parameter space that would actually allow us to form these super Earths with the correct masses. So I would like to talk a little bit now about the ice line. Illustrated here in this cartoon for the solar system, we have our inner solar system that is mainly dry, and in the outer system, you have water-rich, presumably where Jupiter will form. Now, the water ice line is actually very important for the super Earths, because we actually have to care about rocky super Earths or water worlds. And this is a topic that is very hot, so to say, in the exoplanet community, to really discuss if the planets are rocky or more water-rich. And this actually comes from the observations. So you have here in green the Kepler observation. So this is just a normalized fraction as a function of the radius of the planet. So how big is the planet? So in green is the Kepler observations, and you see there's a valley around 1.8 Earth radii. So, and what does this mean actually? You can actually do follow-up observations with radial velocity. So you have the masses and the radius of the planets, then you can run some interior models to actually determine if these planets are rocky or icy in composition. And if you would just assume the planets are all icy, you would arrive at the blue line, and you would see that the valley that you would get is at the wrong position compared to if you assume that the planets would be rocky in composition. So this leads to the idea that the planets, the small super Earths, are actually rocky in nature. So, but what does this actually mean for the formation perspective of these super Earths? So this is a recent plot from Venturini et al. 2020, where they look at the planetary masses against the planetary radius. So in the gray dots would correspond to the observed exoplanet populations. And I would like to focus here mostly on the red dots and on the blue dots. These are the results of their simulations, and you see that they make either small planets, just a couple of Earth masses that are rocky, or water-rich planets that are more massive. In this white line here is the same valley as in this plot here, and they basically conclude that the inner peak of the valley is dominated by rocky planets, and the outer peak might be dominated by water-rich planets. So the idea is that these sub-Neptunes could actually be water-rich. How do you make these guys water-rich? Well, we observe them in the inner edge of the protoplanetary disk. So actually, how do we get them there? And this is due to a process which is called planet migration. And what you have here from the simulations, you have here our planet. It exerts a spiral wave in the protoplanetary disk, so it can exchange angular momentum in the protoplanetary disk. From these spiral waves, you get the Lindblad torque, which normally would push the planet all the way into the star in a very short time scale. Additionally, you have something which is called the corrotation torque, which arises from material that co-rotates with the planet. What actually happens here is you have a temperature gradient in the protoplanetary disk. So if a material that comes from the inner region and is transported to the outer region, it goes from the hot region into the cold region, so it would adiabatically expand and would generate an underdensity. Reciprocally, if the cold material comes from the outer disk into the inner disk, it wants to get to the same temperature, so it adiabatically compresses, and you would generate an overdensity interior to the planet. This density asymmetry then can give rise to the corrotation torque, to the entropy-related corrotation torque that can drive outward migration. And this, very importantly, these torques depend very strongly on the underlying disk structure, so on the temperature gradient, the surface density, and also the viscosity. And basically, I've done a lot of these simulations during my PhD, so it's a topic very close to my heart, where we really try to understand what conditions are needed for planets to actually migrate outwards in protoplanetary disks. Now, what does it actually mean for the water content of these planets? So we can, if you have a protoplanetary disk structure, you can actually calculate a so-called migration map, as you see here on the left, where you have the planetary mass against orbital distance, and the color coding gives you the torque acting on the planet. So if you are above zero, your planet would migrate outwards, as indicated by the arrows. And if your torque is negative, you would actually migrate inwards, also indicated by the arrows. And in red here, that would be the ice line in this protoplanetary disk model. So if you now look at the water content of a growing planet, so we have, in this case, two different planets. So one planet actually starts growing at like 1.5-ish AU, and then it starts growing. You see the color is all in blue, so it creates a lot of water-rich material. It starts to migrate outwards and finishes its assembly in the outer protoplanetary disk. That's then a water-rich planet. And this happens mostly in these disks that would correspond to this migration map shown here, where the viscosity is quite large. But at the same time, if you then would tune down the viscosity, so you would make the viscosity very low, the outward migration actually cannot exist anymore. So your planet starts to grow and it migrates inwards all the way. So basically, it grows, it crosses the water ice and then starts to accrete water-poor material. And you see the colors change in the water fraction, and you actually end up with an inner super Earth that would be water-poor. Well, it still has some water, but it's not as water-rich as a planet that finishes the assembly in the outer regions of the protoplanetary disk. And I want to stress this here, because in the model from Venturini et al., all these dark blue dots that you see here, they have a very high water fraction. This means they finished their assembly exterior to the water ice line and then migrated then inwards. And this really is only possible that if you can retain your planet long enough in the outer regions of the protoplanetary disk. So the important message here is that the migration direction and speed is very important for the planetary composition. So basically how fast you grow and migrate decides the water content in this protoplanetary disk. Now we can take a closer look at our simulations, because I was telling you at the beginning of the talk that the fragmentation velocity of these grains is between 1 and 10 meters. This is of course true, but there's also seems to be an argument between the people that do the laboratory experiments about the composition of the material and what that then means for the fragmentation velocities of the grains. So you see here there are some experiments from Gundlach and Blum 2015 in the lab, where they try to see how the ice grains, the water ice grains, actually grow in the protoplanetary disk. And what they find is that actually water grains can basically stick at larger fragmentation velocities compared to silicate grains. So you would have a transition in the fragmentation velocity at the water ice line. So in the cold parts of the disk, you have the water grains. They can grow larger because they can reach a larger velocity before they fragment. And in the hotter parts of the disk, you have the smaller grains because the silicates have a lower threshold before they would fragment. So the question is, what does it actually mean for the transition, for the water ice line transition for the protoplanetary disk structure? So we model this here. As you see here, we changed just in our simulation the fragmentation velocity for our grain size distribution as a function of temperature. Now we can look at the protoplanetary disk structure. We have here the aspect ratio and the disk surface density. Gray, again, is the position of the water ice line. We use here a low viscosity. So you see here, the two dashed lines correspond to disks that have a uniform fragmentation velocity of 1 and 5 meters. And the solid line has the transition from 1 to 5 meters of the fragmentation velocity at the ice line. And what you see is that you have a sharp bump around the water ice line. And this is related to the fact that in the inner regions of the protoplanetary disk, you have this lower fragmentation velocity, so you have smaller particles. And this means these smaller particles have a larger opacity, so your disk cools less efficient and you're hotter. In the outer parts of the disk, you have a larger fragmentation velocity. This means you go to larger grains, so you get a lower opacity, and this leads to a cooler disk. So you have this so this naturally gives you this transition of the temperature and the aspect ratio, as you see here. Consequently, of course, you get this transition in the surface density, as I explained to you before. Now, what does this actually mean for planet formation? So this bump in the disk aspect ratio actually translates directly into a pressure bump at the ice line position. So you see here the radial pressure gradient as function of orbital distance, and the solid line, that is the disk where we have a transition in the fragmentation velocity at the position of the ice line. So this pressure bump actually means that we can accumulate pebbles at the ice line. And if you have the accumulation of pebbles at the ice line, this actually means you can maybe trap the pebbles there. You can maybe make planetesimals and your first planetary embryos at the water ice line. Additionally, if you look at the migration map, again here, planetary mass against orbital distance, there's a lot of lines in this plot, but you can just focus here on the color scale that gives you the torque acting on the planet. You see actually a very large zone of outward migration at the water ice line. And this also goes basically from 0, basically all the way to like 10, 12 Earth masses. This means the planet that we might form in the pressure bump here at the protoplanet at the water ice line might actually stay directly at this pressure bump and continue to grow before it starts to migrate inwards. So basically the consequence of this is, could this actually really be like a very strong hint that the water ice line might actually indeed be the birthplace of planets? So with this, I would like to summarize my talk. I think it is very clear that it is key to understand the disk structure if you want to understand planet formation in the inner parts of the protoplanetary disks. Additionally, the grain sizes are very important for the pebble accretion rates. So larger grains gives you a faster accretion rate, but at the same time, the larger grains that would give you these fast pebble accretion rates would actually result in colder disk structures. So we have to do the lower pebble isolation mass. So you get you have to see a little bit of trade-off here between how fast can you accrete and what planetary mass you want to reach. The flat aspect ratio of the protoplanetary disks in the inner regions of the disk result in a flat pebble isolation mass, which basically would allow similar planets to form planets from similar mass. And this actually relates to the introduction, where I have shown you from the Weiss et al. 2018 paper that the planets in the same system should have similar sizes or similar masses. Then we studied the change of the fragmentation velocity of the grains at the water ice line, where we found that there's a strong migration trap and maybe even a pressure bump. So the question is, could the ice line really be like the birthplace of planets in these systems? And would we then still have to understand what that then actually means for the composition of these supers? So with this, I thank you very much for your attention, and I'm happy to take any questions.
Thank you, Bertram. Nice presentation, very didactic, very, very clear.
Thank you.
Really interesting stuff. We do not have any comment on the chat. Anybody would like to make a question or a comment, please? Bertrand, I do not have a direct question for your presentation, but something that you probably have seen recently is, well, there is a lot of new data from ALMA and the information coming from there. But I have seen recently about they have imaged the nebula that form the stars, connecting inside the disk, the protoplanetary disk, sending material to the disk from the nebula that formed the star. Have you seen about that?
You mean that you have the infall from the surrounding cloud onto the protoplanetary disk?
Yes.
Yes, we have not taken this into account in our simulations yet. It's of course one of the key things that is missing. So there's of course a lot of.
This is very new. Was it this take? I have never seen any work that take that into account. I think it's something really new, isn't it?
So for the. I'm trying to remember. I think I might have seen one paper. I can try to dig out the reference, but they look at the like from 1D models to look at the infall and then the buildup of the protoplanetary disk itself for planet formation and planetesimal formation. There's some simulations that take it into account, but most of the simulations do not take this into account, and the simulations that I've shown you also does not take this into account.
Okay, do you have any idea how would that change? Because it would be a huge change, I believe. It would be something
well
out of the scope, I think.
Yes, I mean, it's I think it depends how strong the infall is and where the infall is. And I mean, if the infall is, let's say, just in the outer regions of the disk, you might just like continuously dump new material in the outskirts of the disk, so you could make, for example, maintain the pebble flux for a longer time. But at the same time, you might, of course, change the structure of the disk just by the perturbations of the infall itself.
Actually, yeah.
So I think it's something that we have to take into account, and I absolutely agree. I mean, we have to go away from these simple power law disk models that are just smooth power laws. I mean, they are nice because we understand power laws, but we have to really think what we put into these. And these planet formation models are very complex, and I think the disk is something that people have not really thought too much about these models, because there's of course a lot of other things we have to take into account. But the disk in itself really is a key ingredient for planet formation, because the structure in itself changes the migration, it changes the growth, it changes then also the composition of the planet. So yes, I think this is something we have to really start to take a closer look in the future.
Okay. I think, well, as I said, your talk is fantastic. The last question is really intriguing about the last line transition. So,
can I make a question?
Yes, please, Philippe.
Hi, Bertram. Thanks for the nice talk. Very nice. Exactly about the last question. So, I may have lost something here, but you are saying that the planets should, well, form in the transition line of the ice line, but then they would have to migrate, right? And how can we? The point that I may have lost here is about the giant planets. Are you also saying that the giant planets should be formed there, and how they would evolve? You see?
Yes, this is a very good good question. So what you see here in this in this plot here is the migration map from these simulations. So you see the dashed line here is the no wait sorry no the green line, the green solid line, that is the pebble isolation mass. So basically when the planet would stop to accrete pebbles. In this case, this is very low, so your planet would not necessarily grow to a gas giant. But in the simulations that we have in the paper, where we have different disk structures, we can reach higher pebble isolation masses, and the planet would still be trapped at the water ice line position. And then if your planetary core can reach like 5, 10 Earth masses, and is retained in this position at the water ice line, it can start to contract its planetary envelope and then become a gas giant. So I think it's possible. In principle, the water ice line could be, of course, also the birth of giant planets. I did not want to imply that the water ice line is only the birthplace of these sub-Neptune planets. Of course, also giant planets could form there. But then, of course, it depends how fast can you form them, how big is the planetary core that you can make. And if you actually, for example, would make, let's say, multiple cores, they could also collide and then start to undergo runaway gas accretion. So in principle, of course, the water ice line could be the birthplace of many different types of planets, if that already answers your question.
Yeah, I don't see how can we form a complex planetary system with many planets as we are seeing. Because if you have a fast growth of a giant planet like Jupiter, then what we will have left for the others? I may be losing something here.
Yes, no, I mean, it's I agree. If you make a giant planet, things become gigantically complicated. But the thing that you have to keep in mind here, right? These simulations, we don't even put the planet in here. So if you have let's say already 2, 3 small planets, these would start to excite the eccentricities. You can already start to migrate them inwards, because once you actually build up an eccentricity, you lose the capability of being trapped, and there you might actually make a different planetary system. So actually, in this scenario, where you say you make your planets close to the ice line, then you start to migrate inwards, has actually been suggested in this very nice paper from Schonenberg 2019 to actually explain the TRAPPIST-1 system, where you have a lot of planets also in resonance. So they make them all at the ice line, and then they slowly get released to migrate inwards. But this is, of course, based under the assumption that you don't have a migration trap at the water ice line. So I think this is something we really have to understand further from these simulations, if really the water ice line is the first birthplace, and then what actually happens to those planets. I think it's still to some level an open question, and we certainly will continue to work on this.
Okay, thank you. Yeah, I see. we have space to study more further.
Oh, of course.
Yeah, sure.
Of course, I mean, also from the simulations in itself, there's a lot of other things that we can, of course, include.
Thank you.
Okay.
Congratulations.
Thank you.
Anybody else? Any further question or comment? Okay, I think that's it. So thanks very much for your presentation. Very nice work, and the presentation was fantastic, very clear, very easy to follow. Very complex work, as it's clear too.
Thank you.
So Thank you very much. And I think you would like to leave a message now.
Yes. So at the MPIA, we actually have a summer internship program where students are invited to come to the Max Planck Institute in Heidelberg, Germany, for up to 90 days. We normally have 6 internships available. It's normally for bachelor and master students, and the Max Planck pays flight and travel costs and a monthly compensation to cover the living costs. And the students would then then are selected to come here. They can work on projects all over astronomy and instrumentation, so from cosmology all the way down to planet formation. And you can just apply for this internship. We have up to 6 positions available, where the idea is also that we will actually grant at least 2 of these positions to developing students from developing countries, where actually Brazil is one of them. So there's a good chance if you apply that you might actually be selected. You can find the link here on the Max Planck webpage. The call is open since yesterday with a deadline in the middle of January. And you can just look through the projects, and then you can apply. And if you're selected, I will see you in summer 2021.
Okay.
Yeah.
Okay, good. That's great.
Thank you.